Fourth International Physics Olympiad year 1970 IPHO. Problem number 1. A long bar with a mass big M equal 1 kg is placed on a smooth horizontal surface of a table where it can move frictionless. A carriage equipped with a motor can slide along the upper horizontal panel of the bar. The mass of the carriage is small m equal 0.1 kg. The friction coefficient of the carriage is mu equal 0.02. The motor is winging a thread around the shaft at a constant speed v0 equal 0.1 meters per second. The other end of the thread is tied up to a rather distant stationary support in one case, figure A, whereas in the other case it is attached to a picket at the edge of the bar, figure B. While holding the bar fixed, one allows the carriage to start moving at the velocity v0, then the bar is let loose. By the moment the bar is released, the front edge of the carriage is at the distance L from the front edge of the bar. For both cases, find the loss of movement of both the bar and the carriage, and the time during which the carriage will reach the front edge of the bar. Solution for problem 1, part A. By the moment of releasing the bar, the carriage has a velocity v0 relative to the table and continues to move at the same velocity. The bar, influenced by the friction force equal mu mg from the carriage, gets an acceleration force of friction over big mass m, which is mu small mg over big M, and this is 0.02 meters per second, while the velocity of the bar changes with the time according to the law Vb equal at. Since the bar cannot move faster than the carriage, then at a moment of time t equal to 0, its sliding will stop, that is Vb equal v0. Let us determine this moment of time t0, which is v0 over a, and that's equal v0 big M over mu small mg. By that time, displacement of both bar and carriage equal. For carriage, that will be v0 to 0, which is this one, and for bar that will be at0 square over 2, which is this one. The displacement of the carriage relative to the bar is equal to sc minus sb, which is v0 square big M over 2 mu small mg. And after putting numbers, we have 0.25 meters. Since s smaller than L, the carriage will not reach the edge of the bar until the bar is stopped by an immovable support. The distance to the support is not indicated in the problem condition, so we cannot calculate this time. Thus, the carriage is moving eventually at the velocity v0 equal 0.1 meters per second, whereas the bar is moving for the first 5 seconds uniformly accelerated with an acceleration equal 0.02 meters per second, and then the bar is moving with a constant velocity together with the carriage. That was solution for the question A. Solution for question B. Since there is no friction between the bar and the table surface, the system of the body's bar cartridge is a closed one. For this system, one can apply the law of conservation of momentum. We have small m v plus big M u equal m v 0, where v and u are projections of the velocities of the carriage and the bar relative to the table onto the horizontal axis directed along the vector of velocity v0. The velocity of the thread winding v0 is equal to the velocity of the carriage relative to the bar v minus u. That is, v0 equal v minus u. Solving this system of equations, this and this, we obtain u equals 0 and v equal v0. Thus, being released, the bar remains fixed relative to the table, whereas the carriage will be moving with the same velocity v0 and will reach the edge of the bar within the time t equal L over v0, which is 5 seconds. So that was solution for question B. 4th International Physics Olympiad, year 1970, IPHO. Problem number 2. A unit cell of crystal of natrium chloride, common salt, is a cube with the edge length A equal 5.6 multiplied by 10 power negative 10 meters. The black circles in the figure stands for the position of natrium atoms, whereas the white ones are chloride atoms. The entire crystal of common salt turns out to be a repetition of such unit cells. The relative atomic mass of natrium is 23 and that of chloride is 35.5. The density of the common salt, ρ, is 2.22 multiplied by 10 power 3 kilogram per cubic meter. Find the mass of a hydrogen atom. Solution for problem number 2. Let's take a look for this crystal. Here we have edge of this crystal equal A, but it contains 27 different cells. Instead of this, we can take a look for size of A over 2 of this cell. This cell contains only 4 natrium and 4 chloride atoms. All of these atoms belong to vertices of this cell, so it means that each cell belongs to 8 different cells together. It means that the total number of cells which belong to one such cell is 4 multiplied by 1 over 8. And same thing for chloride. So we have 1/2 of natrium belong to this cell and 1/2 of chloride belong to this cell. It means the total number will be this one, which is 29.25 hydrogen atoms. From other point we have total mass of this cell must be equal to ρ multiplied by A over 2 cube, which in our case equal to 29.25 hydrogen atoms. So it means that mass of hydrogen atom equal this number, which is approximately 1.67 multiplied by 10 power negative 27 kilogram. That was solution for problem number 2. 4th International Physics Olympiad, year 1970, IPHO. Problem number 3. Inside a thin-walled metal sphere with radius big R equal 20 centimeters, there is a metal ball with the radius small r equal 10 centimeters, which has a common center with the sphere. The ball is connected with a very long wire to the Earth via an opening in the sphere. A charge big Q equal 10 power negative 8 coulomb is placed onto the outside sphere. Calculate the potential of this sphere, electrical capacity of the obtaining system of conducting bodies, and draw out an equivalent electric scheme. Solution for problem number 3. First, if we don't have any connection of this inside sphere with the Earth, we have potential of this inside sphere equal the same as potential for this sphere on the surface big R. So that will be this one. But because we connected this inside sphere with the Earth, we made this potential equal to 0. So it means that the total potential for outside sphere with the charge Q and the potential of this small sphere with another charge small q together create potential equal to 0 compared to infinity. It means that we have two such potentials, and the total potential will be equal to 0. So we have this equation, and after that we see that small charge q on the inside surface equal this one. Now let's count what is the potential difference between inside surface and outside surface. Because it's created only by a charge a small q, charge a big Q not creating any electrical field inside, we have potential difference equal to this one or this one. And now we can count what is the total capacity of these two surfaces. That will be total charge Q over total potential difference, which is this one, or 44 picofarad. And the last thing, the equivalent electric scheme consists of two parallel capacitors. First one is a spherical one with a charge positive Q and negative Q here, and at the plates and the capacitor sphere Earth with the charges positive Q big minus small q and negative big Q minus small q. So that will be our total electric scheme for this connection. So that was solution for problem number 3. Fourth International Physics Olympiad year 1970 IPHO, problem number 4. A spherical mirror is installed into a telescope. Its lateral diameter is d equal 0.5 meters, and the radius of the curvature r equal 2 meters. In the main focus of the mirror there is an emission receiver in the form of a round disc. The disc is placed perpendicular to the optical axis of the mirror. What should the radius r of the receiver be so that it could receive the entire flux of the emission reflected by the mirror? How would the receiver flux of the emission decrease if the detector's dimensions decreased by 8 times? Directions. When calculating small values, square root from 1 minus alpha approximately equal 1 minus alpha over 2. Solution for problem number 4. As known, rays parallel to the main optical axis of a spherical mirror passing at a little distance from it after having been reflected, join at the main focus of the mirror F, which is at a distance r/2 from the center O of the spherical surface. Let us consider now the movement of the ray reflected near the edge of the spherical mirror of a large diameter g. The angle of incidence alpha of the ray onto the surface is equal to the angle of reflection. That is why the angle OAB within triangle formed by the radius OA of the sphere traced to the incidence point of the ray by reflecting ray AB and the intercept BO as the main optical axis is equal to alpha. The angles BOA and MAO are equal, that is, the angle BOA is equal to alpha. Thus, the triangle AOB is isosceles with its side AB being equal to the side BO. Since the sum of the lengths of its two other sides exceeds the length of its third side, we have AB plus BO greater than OA, which is equal to R. It means that BO greater than R/2. This means that a ray parallel to the main optical axis of the spherical mirror and passing not too close to it after having been reflected crosses the main optical axis at the point B, lying between the focus F and the mirror. The focal surface is crossed by this ray at the point C, which is at center distance CF equal R from the main focus. Thus, when reflecting a parallel beam of rays by a spherical mirror finite in size, it does not join at the focus of the mirror but forms a beam with a radius R on the focal plane. From a triangle BFC, we can write that small r equal BF multiplied by tangent beta, which is equal BF multiplied by tangent to alpha, where alpha is the maximum angle of incidence of the extreme ray onto the mirror, while sine alpha equal d over 2r. So from here we have such expressions: BF equal BO minus OF, which equal to R/2 cosine alpha minus R/2, which is R/2 multiplied by 1 minus cosine alpha over cosine alpha. Thus, we can write that small r equal this expression. Now, let's express these functions through small angle sine alpha. We have 1 minus cosine alpha equal to sine square alpha over 2, which is approximately equal sine square alpha over 2. Cosine alpha equal 1 minus 2 sine square alpha over 2, which is about 1. Sine 2 alpha equal 2 sine alpha cosine alpha, which is approximately equal to sine alpha. And finally, cosine 2 alpha equal 1 minus 2 sine square alpha, which is approximately 1. So, from here we can conclude that small r approximately equal R/2 multiplied by sine cube alpha, which is d cube over 16r square. And from here we can find that small r is approximately equal 1.95 multiplied by 10 power negative 3 meters, which is about 2 millimeters. And from here we can conclude that D is approximately equal this expression. One can see that if the radius of the receiver is decreased 8 times, the transversal diameter d' of the mirror from which the light comes to the receiver will be decreased 2 times, and thus the effective area of the mirror will be decreased 4 times. The radiation flux F reflected by the mirror and received by the receiver will also be decreased twice, since F proportional to cross-sectional area S. So that was a solution for problem number 4.